All right, thank you.
Go for it. Thanks.
Yeah. So hey, I'm disconnected, and I'm going to talk about various interesting and also not bugs case study. So a few words about me. I'm a senior security engineer at Trail of Bits. I also play capture the flag competitions in justCatTheFish team, which I'm a team captain there as well. I work on security stuff, so I also do low-level things and reverse engineering, and I contribute to some open source projects here and there. I also got a blog in the internet, but it's not working currently. So here's the roadmap for today. I'm going to start with cstrnfinder, which was a small research about string-related bugs in C I have made a few months ago. Then I'm going to talk about some Docker leaks related to the sys file system, one of which is was actually a kernel bug related to that allows to bypass kASLR for kernel modules. And I'm also going to talk about some insufficient heap mitigation in glibc allocator. So yeah, let's start with cstrnfinder. And this research started with an idea, or actually thought about the string functions in C. So there are a few functions that work very similar to the strncmp function here shown. So this function actually takes 2 pointers to basically to 2 constant strings, and also a size. And basically, this works very similar to strcmp, which compares the 2 strings, and then it returns 0, -1, or 1, based on the result, whether one of the values is less than, equal to, or greater than 0 when comparing. And the strncmp differs in only that it compares only the first n bytes, or actually at most n bytes, up until a null byte. So that's the difference that was added by adding this argument. So we can see the example here when we compare the some C string variable with a prefix constant string literal and a hard-coded string size of 7. And so if we would start with comparing a string of A with this prefix, we would get -1 because A is actually a lower value than P if we convert it to like ASCII number. Then for the Z itself, we'll get a result of 1 because Z is after P. And then if we try to match the same strings, we get 0. And if we try to match something that is longer but is also prefixed with this prefix, then we also get 0. So the question is, what can go wrong here? And I guess the answer is pretty straightforward. We have this hard-coded value here. Well, the question is, why is it hard-coded at all? Why isn't it derived from a past prefix? Because there might be some issues with when this value is hard-coded in a bad way, not really related to the string literal length of the prefix itself. So yeah, I don't know why it was designed this way, but that's how it is in C, and you have those functions. But some people wrap them in some better ways, I would say. So let's get back to the cstrnfinder. So the idea was actually to find bugs related to those cases. So it all started during one night when I spent maybe 2 or 3 hours manually git cloning like 200 repositories, or basically downloading them from the internet, of various projects, as you can see. And there are also things like GCC or Linux kernel here, and others. And then I started grepping for interesting functions, because as I shown you before, there's this case of strncmp, but there are also other functions that also take the length argument, and they might be broken in similar ways. So that's what I started with, basically. I grabbed all those projects for those regular expressions, as you can see here. And obviously, this regular expression is not ideal because it will miss some cases. For example, when we will have a new line after strncmp and before the parenthesis, then we will miss this case. Another case we will miss is when there will be more than one white space here. I could use an asterisk instead of a question mark here, but I didn't. But basically, yeah. And one good thing about this regular expression is that it might also catch cases where the project itself wrapped one of those functions and called it very similarly. Like, for example, I believe PostgreSQL project had this PG underscore prefix for functions like str and cmp. So yeah, this should detect those cases. And the next thing was that I wrote a Python script to parse the results. And the TLDR for the script is we start with ugly line parsing. So for example, when we have a line like this, when there's an object that is casted to something, and then, or actually a field is first retrieved, and then the field is casted to a type, and then it's also passed to a function, which will in the end return with a character pointer. And then this is also compared to a string literal that sometimes is also casted to something. I don't know really for what, but okay. And there is this hard-coded value. And so we also have to like remove those casts and don't really care about one of those values. And we only want to filter only those cases where we have when one of the arguments is a constant string literal, because we can calculate this length. And when there is also a hard-coded length. I believe I also handled some more complex cases where size of or strlen is used on something that is constant, but I didn't include it here. And in the end, we have to compare the lengths. So we have to compare the length of the constant string literal and the hard-coded length. And let's see what different outcomes we can have. And here's actually an excerpt from the script I have written. So first case, which is a possible bug, is when the string literal length is longer than the hard-coded length. And here's actually an example of one of those cases where the underscore timer colon is actually of length 7, but the hard-coded length is 6. And this was actually a bug in Linux kernel that I found with this technique. But basically, when I find those cases, I am just printing some XXX, the line itself, then the length of the string literal and the hard-coded length. Then I have also cases that I call Z. This is basically arbitrary naming, but in the end, here are cases where we have a length that after adding 1 equals to the hard-coded length. And yeah, basically it takes into account the null byte itself here, or it doesn't take a null byte, one of those. And the last case was the case of Y, which is kind of something that does not spark joy. So those are cases where the hard-coded length is bigger than the C string length, than the string literal length. So we can have we can try to compare with a prefix of like two characters, as we can see on this example here, but we compare it with like 30 bytes. And this actually is not a bug itself, because the function will compare up only up until a null byte. So this is okay, but this is something like maybe some issue like copy-paste bug or something. There was also another case for like debugging, but whatever. And here I got some examples of the results. So for example, for the XXX case, which is probably a bug, we have this case in the LDNS library, in some case.c file, where we have the comparisons. And here we always compare with a hard-coded length of 2. And the strings, the literals that we compare, starts with a digit and then a space and then an algorithm name. And in this particular case, this is not a bug, because the developers wanted to compare just the string itself and not really required to pass in also the algorithm name. And this was, if I recall correctly, this was actually some command line parsing. So cases like this are actually correct, even though they seem bug prone. But yeah, that's how they kind of use this bug as a feature, I would say. Another actually correct case, I would say, is when, for example, GCC had its own test suite and actually tested whether the strings, whether the functions returned proper values. Yeah, and those happened even in like Clang, I believe. And we also come up to some true positives. So, for example, here are some free cases from GCC and also free cases from the Linux code base. And so in the GCC cases, for example, in the first case, they had this .lbss being compared with a length of 5, while the string, while the literal itself has a length of 6. So this is basically an off by 1, probably when expecting a section prefix when processing some ELF file maybe. And so this will match, for example, .lbssx strings. So this is most likely a bug, and as I sent it to them, it was confirmed and it was already fixed. There was very similar case with an of a similar error with another section prefix name, and there was another case with some CF string ref being compared in the darwin.c file with some identifier pointer or something like that. And here they have an off by 3 actually. So this means that we can pass in a string called CF string xxx or basically anything, and it will match here. And so yeah, that's another bug that they fixed. I didn't really look that deep if that was, for example, exploitable or something, but potentially that could have been. And in the Linux kernel, they had even kind of worse cases, like off by 4, when matching some kernel module parameter name in an Ethernet driver in Samsung's driver. Similar case in NVIDIA driver, as exactly with like the setup of the kernel module itself. So this is probably not exploitable or not as much security bug itself. But the last case here is in the perf tools. So they compared prefix for the file name with system // and they compared only 11 bytes, while the constant literal for this path has 12 bytes, which basically means that this check will be passed with whatever path that doesn't end with / here. So if someone would be able to create a directory or maybe a file within system that starts with lib but isn't in the lib directory itself, then this could be exploitable. I believe it wasn't, because the system path is probably present on Android, and I believe it's only owned by root. So I don't think this was exploitable, but still could have been. And yeah, as I said, all those bugs were actually fixed. And there were those Y results, which are really like why someone implemented it like this, but it's still okay. And I didn't really visit much of those bugs because I don't feel it can be used anyhow badly. Maybe if someone changes the code itself to use a longer constant string, but otherwise probably not. And there are those ZZZ results, which includes null bytes. So it seems like they should just use strcmp, but maybe they need to just check for maximum of 5 bytes for some other reasons. I don't know. So I also didn't look into those much as well. But this ended up, I spent like maybe 3 hours just cloning the repositories or downloading them. And it was only 220 repositories. So the question is like, how do we scale it up? And the answer is pretty straightforward. There is this thing called Google BigQuery, and I got this idea from Live Overflow's video, so thanks to him. And Google BigQuery allows us to query tons of data, and there are a lot of public data sets in there. For example, one of them is GitHub repos. And as you can see here, it says it has like almost 3 million public repositories indexed in there. So that's pretty neat. One bad thing is that it says it's last modified at 2019, so that's not nice. But there are other data sets called GitHub Archive that have more data, more recent data. And we can also see this, and here I implemented the query for the Google BigQuery, because you write the query in SQL, so maybe it's not super straightforward, but it's also not that super hard. We basically take two tables, files, and contents, and we join them. And for the contents itself, because the files table is like something that just references the file in the contents table, and the contents table contains basically the contents for given file IDs or file paths. I don't remember. But what I did here is I wanted to be able to filter those contents by something that is meaningful for me. And there is no way to filter based on language, on programming language itself. So instead, I filtered just the contents based on the interesting function names that I want to look for. And afterwards, I filtered those files even further to find all function calls, because then I can parse them and find bugs, basically. So this regular expression here is pretty weird and pretty longish. And the reason for that is in this particular regex engine, as in a lot more others as well, you cannot kind of match the starting and ending of a given parenthesis. So instead, I am matching up to 6 recursive calls within a given function call. So for example, there could have been a line called cstrncmp, where one of the arguments would contain a call, when its argument would also be a call to a function. And I believe this will catch more or less most of those cases, of those function calls cases. I also fixed the kind of issue with not matching more than one white spaces. And this also matches cases with multiple lines, when the call is spread into multiple lines. So this was pretty neat. And for the results itself, I got almost 8 gigabytes of files to process. Then those files had around 33 million records. So basically files containing Cstr function calls. And after filtering, there was only like 2 million results. And later on, after filtering over only XXX results, so those that can probably be buggy, we had almost 300,000 results. And in the end, I also made some more filtering based on some GitHub repository stars and trying to like remove forks and take only the most popular repository, because it ended up that like a lot of the results were coming from forks. For example, of the Linux kernel forks, I believe there were like a few hundreds of them. Yeah. And then I also manually reviewed potentially more interesting cases by grabbing through the 11,000 results. And for those interesting cases, that could have been, for example, strings that ends with a / character, because that's something that could be a path, either a file path or an URL path. And this could be something that maybe you would allow to bypass some checks, or basically exploit something. Then also cases when an extensions are incorrectly matched, for example, .exe with compared to like only 3 bytes, because maybe you could bypass some checks as well. And then when parsing some formats and mismatching some syntax due to wrong size. So for example, I looked for strings that ended with parentheses or XML tags or colons or dashes, things like that, that could have been used in some kind of language or format, because maybe there's some off by one that would allow to do something wrong here. And for the end results, I got around 60 bugs that I reported, and most or all of them were fixed. So for example, there were those 3 bugs in the Linux kernel, which were mostly off by 1, I believe. Or maybe, I think one of those wasn't off by 1. There were 2 bugs in GCC that were, or actually one of them were actually 2 bugs, but reported in just 1 bug report. There was one mistype type name in PostgreSQL. So you could use the JSON to TS vector function, and when you are using this function, you have to pass a type name in a string, and this string can be just string, but you could have typed string X instead of string. There were other issues in some other libraries, like one of the Google input tools library had an off by 1 when parsing XML comments, and this could have been very interesting because you could have cases where such XML would be parsed by 2 different libraries, and one of them would have an off by 1 and incorrectly parse a comment, and another one would not. So you could maybe bypass some, I don't know, XSS auditor maybe. But I haven't really found a use case of this library that would have this bug. So I reported them. I think it was fixed, but yeah. Then there was also an Android bytecode optimizer that had off by 1 with some slash in one of the Facebook projects. Even in one of the Apple projects, there was incorrect path check with an off by 1, which was probably not very interesting because it seemed like it was a very old path that would probably not be used anymore. But the code was still there, and they already fixed it in their open source repository. There were a bunch of others, yeah. And by the way, there was also one funny case which could have been a potential bug there, and that was in Android kernel for LGE phone, I believe. And this repo has like 6 years, so I don't believe it's used and this code is used anymore. But basically, they had this check for debug mode, and this debug on string literal has 7 bytes, but they compared it with 5. And based on that, they enabled this flag here. And another weird case is they had a check for debug off, but this debug off didn't have any logic for disabling debug mode. So that was maybe a backdoor, maybe just a bug. It seems like if you wanted to disable debug and using this debug off command, then you will end up having debug mode enabled. And I have no idea if that particular code path was triggerable by user space or something, but the code was there, so there was a bug like this. And for the research itself, there are still cases that it can't find. So, for example, when you would have when instead of having a hard-coded string literal, you would use a macro definition, or if you would use a constant variable that would be known at compile time, you would not detect those cases with this grabbing approach that I showed you before. And this can be solved with CodeQL, which is a tool from SAML, or actually right now from GitHub. And I have written this CodeQL query that I use from time to time during some like audit projects. And the one issue here is that the code must be compilable, but the good thing is that it resolves things that are known at compile time. It doesn't do any data flow tracking right now, but that's something that could be further improved in here. And I need to basically push it to the official GitHub query repository. But it's there, and I'm not going to demo it here, but you can try it yourself. Yeah, and that's all I wanted to show you for the cstrnfinder research. I will also publish these slides later on, so if you want to like look through some of the results, you can do so. Then the next thing I want to talk about is the Docker leaks for the Sysfile system. And I made this small research with my friend Vesim, and thanks to him for that. But to start with, the Docker itself, when you create the container, it has a lot of mount points. And this is the whole list, except of I commented out some cgroups mounts here. But basically, as you can see, that there's a lot of it. And some of those mounts are actually mounted in a way that you can both read and write files in there. And this is usually meaningful because you might want to access files in your Docker container. But for example, the proc file system is readable, which might not be cool because there are a lot of places there where you could change some configuration of the files of the system itself. Yeah, and plenty others are also readable. And by the way, for the proc file system itself, while it's readable, they disable some paths in there for you by mounting them again with either TMPFS or just proc file system itself, with some options that just doesn't give you any files in there or doesn't give you access to it, or also read-only, as you can see here. And so those paths here are actually in there because Docker manages this list of masked paths, which they add things to this masked paths whenever something can be broken based on that path. And so, for example, there was this case where in the proc asound directory, you could, for example, leak media playback status of the host with the command, as you can see below. So basically, you just spawn the container, and in this container, you read the proc asound card something status file, and this status could tell you whether some music is playing on the host itself. And the similar bug in this proc asound path was with leaking of monitor type. So yeah, that's why they actually disable some of those paths there. And yeah, this is an old bug, and it was already fixed by basically adding into this masked paths. As you can see, this the first path proc asound is this one that caused this bug. But also, I said that a lot of those paths are, or actually mounts are readable, but we don't really need them to be readable to leak something, as you could see in here. And you could actually leak similar things to those reported and fixed already through Sysfile system. And I believe this bug is still not fixed in Docker, but I didn't check in the latest versions. So, for example, if you enter sys class directory, and then some of the directories later on, which we actually print out with the wildcards here, there might be those EDID or WWID files, and they can give you, for example, information on your monitor type or your disk type. And actually, those files are only readable by root. So this bug is only there if you are root in the container, which might be your case, might not be your case, because you shouldn't use root in your containers. But there are also more interesting Sysfile system leaks. For example, you can leak container IDs or name of the services that are running on host. And this actually works without root access. Although it requires some specific setup, but a lot of distributions have this default setup that works here. So the case looks like this. We have this execution of Docker run. When we remove the container, we get into it interactively, and we pass in the user 1000 with a group 1000, just to be sure we don't really, we are not root. And then we execute this command. So we basically want to list files in the syskernel slab something, then cgroup directory. And we process this line with like sort, unique, and just list the tail of it. And as you can see here, we are seeing some services that are being listed here. And those services are actually running on the host. They are not present in the container itself. But we have these names of the services that are running on the host. Then we can also get names of the other container IDs, because it seems like there is this directory called UTS namespace with probably the namespace name for the container, but the namespace name for a given container is just its ID. So we are getting this ID here. Another interesting thing is that we might get some information about sessions that are running on the host, so user sessions, for example, but this might not, during my test, it doesn't work everywhere, so I'm not sure what's the certain condition or constraint here. The question is, why does it even work? Like, why are there some directories that give us such information? Because we can't really read data in those directories when we are not root, but we can read the directories names because that's how those permissions there work. And so this is because it's some debug information, and this debug information, in order to be enabled, it requires the slab memcg sysfs on kernel compilation option, and you also need memory cgroup controller being enabled. So the latter condition, memory cgroup controller enabled, is usually, you usually have it in your Linux kernel. The first condition, slab memcg sysfs on the kernel compilation option, you might not have it, but if I recall correctly, Ubuntu still has it. So you might have this leak on your system. And the thing is, we can actually also monitor this live. And I want to thanks to Felipe from Trail of Bits for the payload for it. And we can actually see it on a short demo. So I am SSH to another Linux machine where I am running this Docker run command with this like finding all the files in the sys, putting them in the initial file path. Then in a loop, I am basically snapshotting a date with this find, and then I am comparing the last and new results, and I'm removing the last, like swapping them or something. And let's run this. I'm actually running here as a root, but it would also work without root. Maybe I can add this here. Yeah, I think it was -u. Oops, missing space. Oh, and there needs to be a, yeah. Oh, wait. Do I need one? Oh. Oh, yeah. Okay, never mind. I have it right now. Okay, what's going on in here? Why do I have permission denied for a file? Is it not running in a container? Let me try again. Or maybe let's try it. I'm pretty sure it works without root. Maybe there's some problem with the file path I'm saving to. I'm not sure here, but this should work without root as well. Anyway, so now I am, for example, let's start. So here we are on the container, and we are monitoring this those directories. And now let's try to actually launch some service. So let's do, for example, launch Nginx. So if we launch Nginx, we'll actually get a lot of directories, a lot of those debug directories for the Nginx service, and we can actually see it in the div itself. If we also try to like Docker run another container, we will also see it here with the container ID. As you can see, the container ID actually starts with this ID that is being leaked. So that's basically the container ID. And we can basically monitor what's going on the host system, look what container IDs are being spawned, what services are running, and so on. So this can be interesting for an attacker if they want to like exploit some other service that is running on the host, but they have only access for the container. And there is yet another leak that turns out to be a kernel bug, as I said, and it's kernel modules addresses bypass, kASLR bypass, actually. So there is this sys module overlay directory, and by the way, this one actually requires root access, but it's still a bug which we'll see in a moment. So basically, there's this sys module directory, which we can actually see here. It contains directories for all the kernel modules that are loaded, or most of them. Most of them, I'm not sure if for all, but I believe that probably yes. And then in some of those, there might be the sections directory, which have the name of the sections present in the binaries for those kernel modules, and those contain addresses. And here I have a kernel that has this bug fixed, so I don't really see those addresses here. But in the previous kernel versions, we could see those addresses here. And so, yeah, we can actually get all of those leaks this way with cutting all these modules and their sections. And so the question is, what was the bug? And it's probably worth to mention that normally you can read kernel module addresses via the proc file system. Proc file system itself. There are those files called modules and calsims. But if we try this on Docker, the addresses will all be zeros, as you can see here. The addresses for the calsims and for the modules are all zeros. They are basically removed from us because we lack certain permissions, even though we are root user. And the reason why we are not having permissions is, or we are not seeing those addresses, is because we lack the kASLR Linux capability, because the root privileges are spread into capabilities, and Docker disables some of those capabilities by default. And so we can't really leak those addresses. We might leak actually the layout of those symbols, but we can't leak the addresses itself. And we can actually leak them if we add the kASLR capability, as you can see here. And there is one catch. If we had kernel.kptr restrict equals 2, which is a kernel runtime parameter, we would have zeros being returned here as well. But sadly, this option is not a default, for example, on Ubuntu, as I recall. But this was not the case here, because we didn't have the kASLR, and we could still see the addresses. And actually, the conditions for the bug to work is that the kernel kptr restrict had to be lower than 2. So it could be either 1 or 0. The slide is broken here. We had to be root, and we don't really have to have the kASLR capability in order to see those addresses. So basically, the bug is that the kASLR capability should, the lack of the capability should disable seeing of those addresses, but it's not the case here. And the bug fix for it was kind of straightforward, but not really. The bug was that they had this check for this restrict value being less than 2, instead of using appropriate, like considering other factors like capabilities. So this is the commit that fixed this bug, but actually they also refactored some of the other code to have, for example, this function calsims show value, I believe, or maybe there was there. Anyway, I reported those bugs to Docker and Linux kernel, and we can see the timeline here. So I first reported the bugs to Docker, and I got reply that they will probably fix it via using the mask paths, and also that the memory addresses should be reported to the kernel devs, because I wasn't sure that it's a kernel bug at first. And then I also informed the security at kernel about this kASLR bypass. I also investigated it myself, and the bug was confirmed by Keyscook, and then there was this discussion between him, Greg, and Linus as well, which was kind of nice about how to fix that. I also asked Docker for an update in the meantime, and later the kernel got patched for this issue. And then I also pinged Docker again, informed them that the Linux bug was fixed. And in this month, like 2 weeks ago, I asked Docker for an update, but I didn't get any update from them. So I have no idea if that's fixed, but I informed them that I am going to disclose those bugs here, because maybe those bugs are not as impactful for them to fix them. I don't know. The last thing I want to talk about, even though I have probably 5 minutes left, is glibc heap corruption detection and like some security mitigation. And of course, I want the full glibc heap 101 here because there is no time. But TLDR is that in glibc, there is this struct for allocated memory chunks. And this struct is called malloc chunk. And it starts with this pref size and size fields, which are of type internal size t, which is actually size t. And it's usually 8 bytes on 64 bits. Yeah, for example, the size, it's actually the size field here also contains some flag bits, which is irrelevant here, actually. But then, whenever you are allocating something, the malloc actually doesn't return an address of the malloc chunk. It actually returns you 16 bytes past it. So it returns you the address of the FD field itself. And whatever you put there overrides all those other fields because they are not really used whenever the chunk is allocated. Those fields can be reused whenever the chunk is deallocated in some cases. But before your allocation, you have this pref size and size fields, which is important here. And there are also one thing I want to mention. There is this feature called fast beans. So whenever you are freeing something, malloc is actually holding those freed pointers in some linked list called beans. And one of those linked lists is actually a fast bean. And these fast beans can have given size or actually also like given fast bean index in the end. And when we have a equals malloc of x, then we free the a pointer. Then we also allocate x bytes, but assign it to b. Then malloc will actually return us a pointer, the same pointer as a, because it basically cached the freed pointer to be returned to us later on in order to not free this memory into this file, into the operating system itself, because that would probably be slow. So malloc is kind of managing the memory that the system gave to it and trying out to make it fast. And in the end, when we do something bad, like change some internal metadata for the given allocation or actually deallocated chunk as well, or which we call bin, the malloc or free will feel bad, which basically means it will probably detect the corruption and crash the program. This is helpful for developing and also for this is also a security mitigation here. So the bug is pretty straightforward. There's this int malloc function, and somewhere in this malloc function we have this check for the, well, it starts with well, it doesn't start, but somewhere in this function we have this check whether the size for the allocation is included in the fast beans. And when it is the case, we are getting this fast bean index in the first line here. Then we are also grabbing some victim, which is, I believe it's an either next pointer or the first pointer. And later on, we do a check over this victim. And this check uses the chunk size of the victim and then fast bin index of this chunk size. So let's see what the chunk size does. It basically takes the size, removes the size bits values, and takes this size in the end. Then it takes the index of the fast bin. And this fast bin index, it actually does some like shifting here, but it doesn't matter. The shifting itself doesn't matter. What matters is that the size field is of a type of size t, which is 8 bytes on 64-bit architectures. But we are casting here into an unsigned int, which is usually 4 bytes on 64-bit architectures, which basically means that if the size is corrupted in a way that this value will overflow, then we won't really detect the corruption. So in the end, there is an overflow used for corruption checking. So I would call it's not a bug, it's a feature. Actually, this feature is used for exploiting CTF tasks and probably also somewhere else, basically to place a fake deallocated chunk or allocated chunk when we can't fully override the size value, when we have some heap overflow or something like this. And I didn't report it myself yet, but I will do so. But maybe it's in the bug tracker. I don't know. This bug is most likely known by a lot of people because a lot of CTF players use this as an exploit vector for heap bugs. But I don't know if the upstream knows about it. But it can be easily fixed by changing this one cast line to use size t type instead of unsigned int. And to sum up my presentation, you can find a lot of stupid C bugs with just normal grabs, but while the talk wasn't about, you should probably also see samgrep and CodeQL projects because they are probably more useful than normal grep. And also Docker wants to isolate you from the host, but the way it's designed doesn't really allow for full isolation, I would say, because there are all those mount points that can leak a lot of data, information about the host. And you might also sometimes find stupid bugs in kernel that probably wouldn't be a big deal without containers, because you would need special conditions like lack of this syslog capability and also be a root on the system. And also security mitigations may also be broken, for example, in glibc. So that was all for my presentation. Thank you very much.
Sorry, just adding everyone back into the stream. Thank you so much, Dominik. That was an excellent presentation. And I think I've got everyone on here. No. Stefan, I'm adding you because I'm sure you have something to say.
Well, no, I mean, I actually watched Dominik as he was developing this, so it's I don't have questions because we talked about it, but I do think Dominik does lots of really interesting things in the Linux space here. It's basically what we tap him for on all the assessments. If you're interested in some of the other things that Dominik has found, he's also found a whole bunch of interesting bugs in Kubernetes itself. Dominik was one of the 3 people, along with myself and Bobby, who's also been on Absolute AppSec, who you know, were actually doing the Kubernetes assessment, and Dominik mostly focused on like Linux C group stuff and Linux more generally, and found all sorts of interesting things. So this isn't his first rodeo, but very interesting bugs always in that sort of space.
Great. Yeah, I don't think we necessarily have any questions. There's been a couple of comments that have come in, mostly just saying good job, Dominik. Super informative. So we'll kind of let you take that offline, and we'll get it posted as well with all the other talks. We appreciate you giving the time to us though for the conferences. And yeah, anything else from organizers? Ken?
Thank you for staying on late, Dominik, since Dominik is in Europe and it's it's so late.
It's almost 11 p.m. here.
Yeah. Oh, thank you.
Yeah, thank you.